At an air show, an F-22 Raptor can point its nose toward the sky, slow until it appears to hang in place, then turn in a way that seems to ignore ordinary flight. It has two engines, flight computers, radar-absorbing skin, and thrust-vectoring nozzles. It is one of the most advanced fighters ever built, but its deepest problem is ancient. How do you make a surface in moving air obey you? That question was visible thousands of years before fighter jets. It was visible in a bamboo frame covered in paper or silk, pulling against a line in the hands of someone on the ground. The first answer was a kite. This is not a story in which a Chinese kite literally became an F-22. The Raptor came from engines, metallurgy, aerodynamics, electronics, and generations of flight tests. The connection is more interesting than a fake family tree. Across every stage, people kept confronting the same enemy. Air gives lift only on its own terms. The long road to the F-22 is the story of taking those terms back. The Smithsonian places the invention of kites in China in the 5th century BCE. Chinese kites in its collection use split bamboo, paper, silk, paint, and twine. Those are simple materials, but together they make a tiny flying machine. Bamboo supplies a light structure. Paper or silk provides a surface for the wind to press against. A bridle sets the angle of that surface. The line gives a person on the ground a connection to the result. That connection matters more than it first appears. A kite is not merely something that rises, it is a visible negotiation with moving air. Pull too hard and its angle changes. Let out line and the load shifts. A gust can make it pull, tilt, climb, shudder, or collapse. You do not need equations to notice the cause and effect. Your hands feel it. The early kite made an invisible force legible. Every important flight control system that followed would face the same variables: surface area, structural weight, angle to the flow, stability, and the lag between an input and the machine's response. A child flying a kite sees none of those labels, but the machine teaches the lesson anyway. A wing is never just a wing. It is a wing in an argument with the wind. And at this stage, the wind is winning. The operator can influence the kite, but cannot command it with precision. A gust changes the angle. The surface catches too much force. The kite yanks, stalls, spins, or dives. Anyone who has watched a kite disappear into a tree has seen the primitive version of the problem that would dominate aviation. Air is useful only if it is controllable. For centuries, that limitation was acceptable. A kite could be a craft, a signal, a toy, or a spectacle. No one inside it needed to arrive at a chosen place. Then people asked it to do a job where losing control had consequences. In Britain, during the 1890s, Captain B.F.S. Baden-Powell experimented with man-lifting kites. The Royal Engineers formed a kite section. Samuel Franklin Cody took the concept further with a train of lifting kites, a winch, and a basket. By 1904, he was demonstrating the system to the Army at Aldershot. The appeal was obvious. A soldier raised above the ground could see past a ridge, a wall, or a line of trees. Before reconnaissance aircraft were reliable, height itself was intelligence. The kite system offered it without an engine. It used the same force a child had felt in a string, multiplied until it could carry a person. But a military use made the flaw impossible to ignore. Cody's observer could look. He could not decide to fly around a hill. He could not hold a chosen course as the wind changed. He could not descend on demand if the weather withdrew its permission. The basket was an elevated observation post, not an independent aircraft. That distinction sounds obvious now, but it separated two futures. One future pursued bigger lifting surfaces, stronger lines, and more reliable winches. It could make an observer higher. The other had to solve a harsher problem, put a human inside the flying machine and give that human authority over its balance. Scale made the limitation clearer. More kites could create more lift, but they also created more line, more drag, more dependence on wind direction, and more ways for the entire arrangement to become unmanageable. The observer was cargo attached to a weather system. That is not freedom of flight. It is a temporary permission slip from the atmosphere. The missing ingredient was not courage or power, it was control. The first airplane problem was never merely getting off the ground. It was making sure the machine did not choose its own direction once it got there. Wilbur and Orville Wright did not begin by bolting an engine to a wing. They began with balance. An aircraft can rotate in 3 basic ways. Pitch changes where the nose points up or down, yaw swings the nose left or right, roll tips one wing down and the other up. Of those 3, roll was the immediate danger. If a gust made one wing lift more than the other, the aircraft banked. Without a way to correct that bank, a pilot was not a pilot. He was a passenger waiting to be overturned. In 1899, the Wrights built a 5-foot biplane kite to test an answer. The Library of Congress records that it was made to test wing warping. 4 lines connected its outer structure to hand sticks. When the sticks turned in opposite directions, the wings twisted. One wingtip met the air at a higher angle and made more lift. The other did the opposite. That sounds almost too modest to matter. Twist a little kite, change the lift a little. But the idea rearranged the whole relationship between a flyer and the wind. The point was not to make a larger kite. The point was to create unequal lift on command. Think about what a turn requires. A machine cannot simply slide sideways through the air like a car turning on pavement. To turn efficiently, it banks. Once banked, some of its lifting force is directed sideways, curving its path. But banking is dangerous if it happens accidentally. The Wrights' insight was that the dangerous motion and the useful motion were the same physical event. The difference was whether the pilot caused it deliberately. The kite gave them an inexpensive fast feedback loop. They could manipulate a surface, watch the response, feel tension in the lines, and change the mechanism before placing a person inside a larger machine. That is the first serious bridge to a modern fighter. Not a shape, not a material, but a control input translated into an aerodynamic consequence. The next step was brutal because the kite did not solve everything. A small, flexible structure can tolerate behavior that becomes dangerous as size, speed, and weight increase. The Wrights' early gliders did not produce the lift predicted by the data they had borrowed. Their 1900 and 1901 experiments also revealed another difficulty. When wing warping began a turn, the aircraft could yaw in the wrong direction. This was the moment when aviation could have become a collection of clever demonstrations. The Wrights had proved that a wing could be manipulated. They had not yet proved that a whole aircraft could be controlled. The gap between those 2 statements is where engineering begins. For a less stubborn pair, partial success might have been enough. The public could see gliders. The kite had responded, but the numbers were wrong, and the sky does not care how promising a prototype looks. So the Wrights built a wind tunnel in their bicycle shop and tested their own small wing surfaces. This is one of the quietest revolutions in the story. The famous first flight is dramatic. The wind tunnel was more important. Inside that wooden box, air became something they could measure instead of merely endure. They compared shapes. They observed forces. They replaced inherited assumptions with results that belonged to them. The logic had changed. First came an effect. The glider did not behave as expected. Then came a test. Isolate the surface and expose it to a controlled stream of air. Then a mechanism. Change the shape or angle. Then another test. That loop is familiar in every modern aerospace program, even when the wooden tunnel has become a supercomputer, a full-scale rig, or an instrumented test flight. The Wrights also confronted a problem that still haunts aircraft designers. Controls interact. You can ask for roll, but the air may answer with yaw. You can correct one motion and create a second. Their solution was to link the rudder to the wing warping control so a turn did not leave the tail fighting the rest of the machine. That was not an ornament added after flight had been solved. It was an early control system. A pilot moved one command, several aerodynamic surfaces worked in coordination, and the aircraft produced a usable turn rather than a chain of accidents. Notice the progression. The ancient kite revealed the force. The man-lifting kite proved that raw lift was not enough. The Wright kite showed that unequal lift could be commanded. The wind tunnel showed that command had to be measured, and the coupled rudder showed that a flying machine is not a collection of separate tricks. It is a system whose parts must agree before the pilot can trust it. Wing warping was ingenious, but it asked an entire wing to twist. As aircraft became larger, faster, and structurally stronger, that became increasingly awkward. Designers kept the function but changed the hardware. Instead of flexing the whole wing, they moved smaller surfaces at the trailing edge. Those surfaces are called ailerons. An aileron works through the same core argument as wing warping. One side moves so that one wing produces less lift. The other moves so that the opposite wing produces more. The aircraft rolls. The solution is no longer a flexible kite-like wing, but the purpose is unchanged. Create a difference in lift at the exact moment the pilot needs a bank. That is how progress often really works. A mechanism survives while its body changes completely. Bamboo becomes metal. Paper becomes engineered skin. Hand sticks become cables, rods, hydraulics, and electrical signals. The visible object is transformed, but the problem it solved remains stubbornly familiar. The move to distinct control surfaces also made the relationship between structure and control more manageable. A wing could be designed to carry load while a smaller, dedicated part moved to alter the airflow. It was a practical separation of jobs. The main surface holds the aircraft up. The control surface tells it how to move. By the time aviation moved from experiments to large machines, pilots were no longer trying to persuade a loose fabric surface to cooperate. They had machines built around controllability. Yet greater speed did not remove the original problem. It intensified it. At high speed, small changes happen quickly, forces become severe, and a pilot has less time to detect and correct a mistake. That is why the lineage from kite to fighter is not a museum curiosity. The more powerful the aircraft became, the more valuable precise control became. Power without control only makes failure arrive faster. There is a second lesson hidden in that transition. Every advance in flight creates a new version of the control problem. A light fabric wing can flex, which makes warping possible but makes the structure less predictable. A stronger wing can carry more load, but it needs a different way to change lift. A faster aircraft can travel farther and respond more sharply, but it gives the pilot less time to understand a bad motion. The solution is never simply to add power, it is to make the response legible and repeatable. That is why an airplane's controls are not an accessory. They are the bargain that makes the rest of the machine usable. An engine may create thrust, a wing may create lift. But without a reliable way to alter the balance of forces, both are potential sources of danger. The Wrights understood this before powered flight had earned its mythology. Their question was not, can we make something leave the ground? It was, can we make it come back under our authority? The answer became progressively less visible to the passenger. On a kite, the operator can see the line and feel the pull. On an early glider, the pilot can see the wing flex. In a modern fighter, much of the work happens through systems that are too fast and too interconnected to follow with the eye. Yet the physical conversation is still there. Air presses on a surface. A control changes the surface's relationship to that air. The aircraft moves. The difference is that the Raptor can make the conversation happen at speeds and forces that would overwhelm a human reacting alone. That is the real escalation from the kite. It is not from simple to complicated for its own sake. It is from a person responding after the wind moves the machine to a system designed to make the machine respond when the person decides. It is tempting to tell this history as a parade of better machines, a kite, then a glider, then an airplane, then a fighter. That version misses the tension that makes the chain meaningful. At every stage, adding capability made control more difficult to earn. A kite has almost no independent authority. Its operator can change the line, but the wind supplies nearly every important condition. A man-lifting kite adds a human payload, which raises the stakes without giving that payload much freedom. The Wright's kite adds a deliberate change in lift, but then exposes the need to manage the rest of the aircraft's motion. The larger the machine becomes, the more its structure, speed, and momentum resist simple solutions. That is why the first control innovations often look unimpressive beside the machines they eventually enable. A twisted wingtip is not visually dramatic. A linked rudder is not visually dramatic. A hinged aileron is not visually dramatic. But each one changes the status of the person aboard. He is no longer merely being carried by a force. He has a way to negotiate with it. This distinction matters because flight is full of machines that can produce lift for a moment. A gust can lift a leaf. A balloon can rise. A kite can carry a camera. None of that automatically produces an aircraft that can go where its pilot needs, stay there, and return safely when conditions become difficult. Useful flight requires a continuous chain of authority, sensing what the machine is doing, choosing a correction, producing a physical response, and avoiding a new problem in the process. The Wright's work makes that chain visible before it disappears into modern systems. Their kite was a test. Their gliders created evidence. Their wind tunnel measurements corrected assumptions. Their coordinated controls responded to the interaction between roll and yaw. The method was as important as the invention. Treat every surprise from the air as information, then redesign the machine around what the air actually did. By the time a modern fighter reaches the sky, that method has been absorbed into the aircraft itself. The pilot still has an intention. The atmosphere still has its own behavior. Between them is now a carefully designed translation system. The machine receives a request, coordinates controls, and tries to give the pilot the motion that request meant, rather than the uncontrolled motion the air would otherwise impose. That is the point at which the old pipa stops looking small. Its importance is not that it resembles a fighter, it is that it makes the original conflict impossible to miss. Lift without authority is only a beautiful accident. The F-22 Raptor sits at the far end of that escalation. According to the U.S. Air Force, its flight control system controls the thrust vectoring nozzles, horizontal tails, rudders, and wing surfaces. The aircraft does not rely on one moving piece to answer the pilot, it coordinates several. That coordination is what makes the Raptor's most startling movements possible. The pilot is not manually calculating every surface angle while the aircraft moves through changing air. The flight control system interprets the requested motion and commands the aircraft's available controls together. The result may look like a single, impossible gesture. Pitch hard, maintain authority, redirect the nose, recover with precision. The thrust vectoring nozzles are especially revealing. A conventional control surface changes airflow over the aircraft. The Raptor can also direct engine thrust to help produce a change in pitch. This does not erase the old aerodynamic problem. It adds another tool to the same job. Make the aircraft respond predictably when the pilot asks. Look at the chain in that light. The kite's bridle set an angle to the wind. The Wrights twisted a wing to change lift from side to side. Ailerons concentrated that change into hinged surfaces. The F-22 system coordinates surfaces and thrust together. Each step increases speed, force, and complexity. Each step also tries to close the same gap between human intention and atmospheric reality. The Raptor is not controlled because it has more technology. It is controlled because the technology is arranged around a clear priority. The pilot's command must arrive at the airframe as a stable, useful motion rather than an overcorrection, a skid, or a loss of authority. That priority is easy to miss at an air show because spectacle hides the engineering. When the aircraft seems to pivot, the visual drama is not simply brute engine power, it is coordination, flight control logic, aerodynamic surfaces, thrust direction, structure, and the pilot's input all arriving at the same answer before the moment is gone. So how did an ancient kite become the F-22 Raptor? Not by a straight line of inventions, not because a kite contains a secret fighter jet waiting to be enlarged. It became the F-22 by exposing the first version of a problem no aircraft designer could escape. A kite makes lift visible. It also makes instability visible. It teaches that air can hold a surface up and, in the next gust, take command away. Cody's military kites showed that lifting a person higher did not make that person free. The Wrights turned a kite into a test platform for deliberate roll control, then refused to accept bad data or uncontrolled yaw. Ailerons preserved the key function as wings became stronger and faster. The F-22 coordinates that same function across an entire aircraft adding thrust vectoring to the pilot's authority. The distance from bamboo and paper to the F-22 is not measured only in years, engines, or money. It is measured in how much of the wind a human learned to command. And the next time a kite pulls against the line, look at it differently. That small tension is the first bargain in aviation. The wind supplies the force. The machine tries to make it answer.